A conic section is a curve obtained from the intersection of a plane with the surface of a cone. Basically, you take a plane and you slice a cone with it, and then when you do that, there's going to be a figure that's created at the intersection of the two geometric objects, and that figure is what we refer to as a conic section. Now, depending on the angle at which you cut the coin or slice the cone, you're going to come up with a different kind of conic section. The main ones, as you can see, are the ellipse, the parabola, and this two-piece curve known as the hyperbola. Now, if you happen to slice it in a way that cuts it right at the point where the two naps of the double cone meet, then, for example, you would end up with a point. Or if you slice it just at the edge like this, you would end up with a line. Or if you slice it in a similar way to where the hyperbola was slicing it, but go all the way to an extreme 0-degree angle, then you would end up with a pair of intersecting lines. So because these three conic sections are clearly very simplistic and not as interesting as these other three, we call these degenerate conic sections. Now, it's not quite meant in the same way that the word is meant in regular English. In mathematics, basically, a degenerate case is a limiting case of a class of objects which appears to be qualitatively different from and usually simpler than the rest of the class. So this would be the regular class of conic sections, and to distinguish them from these so-called degenerate conic sections, we call them non-degenerate conic sections, and these are the ones we're interested in studying. And these, of course, are very familiar to us, and we've studied them already. In fact, some people consider a point to be a circle of radius 0, but mathematically speaking, we don't like to go in that direction because of the limitations it would put on some of the theorems we have about circles. But that is definitely one way you can think about a point. Given that the angle at which you're slicing the double cone is so important, we want to take a minute to talk about that next. Firstly, the kind of cone we're dealing with is what's referred to as a double napped cone. It's spelled N-A-P-P-E-D, but pronounced N-A-P-T, double napped cone, because it has two naps. We call this one the upper nap and this one the lower nap. There is a central axis that goes through it, which is called the axis of the cone. And there is an angle which the generator makes with that axis, which is called the vertex angle. Notice that basically we fix that point and the angle, and then we rotate 360 degrees to generate the entire cone. And of course, remember that this generator line is it goes on ad infinitum in both directions. So the cone that it creates is also an infinite cone. So the cone would be going on forever on the top and the bottom as well. But we always show just a slice of it for simplicity of viewing, of course. The kind of conic section that results from the cut, as I said, depends on the angle of the cut. So if the vertex angle is called A and the cut angle is called B, which is basically the angle between the plane and the axis of the cone, then depending on the size, we get a different object. For example, if the angle of the cut is greater than the vertex angle, and of course up to 90, you end up with an ellipse. Now, Some people consider circles to be a different kind of conic section, but if you think about it, a circle is just a special case of an ellipse. So we don't like to categorize that as a separate kind of conic section. The correct way of classifying them would be as an ellipse. So therefore, a circle is included in this group. Notice that I say less than or equal to 90 degrees. If it's exactly a cut at 90 degrees, you end up with a circle. For the parabola, you obtain that when the angle of the cut is exactly the same as the vertex angle. Then the object that you will see at the intersection will be a parabola. And if the angle of the cut is less than the vertex angle, you're going to end up crossing both naps of the double napped cone, and you end up with one a cross section here and one cross section here, but together they form one geometric object called a hyperbola. So remember, that happens when the angle of the cut is actually less than the vertex angle, but obviously greater than 0. If it is 0, we get a special case of the intersecting lines, which we spoke about, which was one of the cases of the degenerate conic sections. Let's go ahead and take a look at a simulation which does a really great job at this, and will explain it in a much more interesting visual way. All right, here we have this really amazing app created using the wonderful GeoGebra application by Tabitha McAfee and R. Ramanujam. And notice that what we have here is a double napped cone with a vertex angle, which is the angle between the generator and the axis of the cone, of 35 degrees. And notice that when the angle of the cut relative to the vertex angle is greater than the vertex angle, you end up with an ellipse. So here is the visualization on the objects themselves, and here's what you end up with shown separately here. Very nicely done. Now notice that the position of the plane that is cutting is going to make a difference as well. So for example, if I take this to 35 degrees exactly, you know that when the angles are equal, we should get a parabola, right? And we do, right? But notice here's an extreme case. If I actually do so, but position the parabola exactly at the, so that it goes through, it just touches it at just one point here at the center, watch what happens. So when we position it so that the plane is touching both naps as well as the vertex of the parabola, the cross section is going to be one of our degenerate cases, right? It's going to be just a straight line. All right, now we know that if the angle is going to be greater than less than, we already covered the greater than. When it's greater than, we end up with the ellipse, right? And then at 90 degrees the circle. But let me show you that real quickly. There it is. Now of course, because of where I've placed the plane right now, that's one of our degenerate cases. But if we slice it at any other point other than the vertex, watch what happens. You end up with a circle, see? Okay? So now let's take a look at the We've already seen the ellipse, right? All those are ellipses, right? Now let's go to a situation where the angle of the cut is actually less. For example, here's a 15-degree angle, right? Now, again, if this happens at an extreme position, then that's when you get your two intersecting lines. So we bring the angle all the way down to 0, see? All the way down to 0, and if you look at the cross section, you end up seeing this degenerate case of two intersecting lines. And if you were familiar with the equation of a hyperbola, you would see how that changes, but we haven't done that yet. So just for now, this is the visual that I wanted you to see. That's how you end up with the two intersecting lines. So this is a really nice graphic. If you want to search for it and play around with it, you would gain a lot of benefit from doing so. Really helps you understand how varying the angles, etc., and also the position of the plane makes a difference in the objects that are created. All right, so that should be helpful as a visualization of how conic sections are created by slicing the double napped cone. All right, next we want to go ahead and take a deeper look at this kind of a conic section, a parabola, which we're already familiar with. We're going to look at horizontal parabolas as well as a new way of defining the parabolas using what is known as the focus and the directrix. The last thing I would like to bring to your attention before we leave this screen is that the ellipse and its special case, the circle, are closed curves, whereas the parabola and the hyperbola are open curves. We're already quite familiar with this type of parabola, which we call an up-down or vertical parabola. The equation of this kind of parabola can be expressed either in standard form as y equals ax squared plus bx plus c, or in vertex form as y equals a times quantity x minus h squared plus k. Once it's represented in that form, we can quickly extract the vertex from that form to be hk. And we know the axis of symmetry will be the line x equals h. And we know that if the coefficient a of the lead term is positive, then the parabola is going to open upward. And if it's negative, it's going to open downward. We know that these kinds of parabolas represent functions because they do pass the vertical line test, as you can see. And the reference up-down parabola is y equals x squared. By that, we mean the parabola that we compare the other parabolas to. Is it narrower than this parabola? Is it wider than this parabola, etc.? Especially when we want to do transformations of functions. Now, it can be shown in a very similar way that the left-right parabolas, known as horizontal parabolas, have a very similar equation. The standard form for such parabolas is x equals ay squared plus by plus c, and the vertex form is x equals a times quantity y minus k squared plus h. As you can see, these do not represent functions because they fail the vertical line test. Almost any vertical line that you draw through them will intersect them at 2 points, right? Except, for example, this line right here, which the vertex intersects at only 1 point, but all the other vertical lines that would intersect it would do so at 2 points. So it is not, these are not functions, they are relations. So we say they represent non-function relations. The vertex, once again, is hk, and the axis of symmetry, of course, is horizontal. It lies at the line y equals k. If a is greater than 0, these will open toward the right or rightward. And if a is less than 0, these parabolas open leftward. The reference left-right parabola is x equals y squared depicted here. We have seen plenty of up-down parabolas, so we're going to take a look at a few left-right parabolas for now. So let's say we want to graph this particular parabola written as x minus 6 equals y squared, and find the vertex, axis of symmetry, and the domain and range. So remember that this type of parabola where the square is on the y rather than on the x is going to be a left-right parabola. The most useful form, of course, is the vertex form, which is x equals a times y minus k squared plus h, right? Now, if I take that and write it in this form exactly, it would look like this, right? X equals 1 times y minus 0 squared, and then move the negative 6 over to the other side, and you would get that. So we can try to graph this in two ways. We can talk about what transformation is needed to the graph of the reference left-right parabola x equals y squared. Notice that there's no change in y here, but the parabola is being moved 6 units to the right, right? Because notice the change in h is going to be a horizontal change, right? And there's no shift up or down, so because it's y minus 0 squared. So we can just take basically this parabola and move it 6 units to the right, and we end up with the graph of this parabola. All right, so the other way, of course, is to go ahead and plot some points. Basically, 3 points should be good enough because we know what it's going to look like. So now what we'll do is we'll start as usual, the way we did with up-down parabolas. The most efficient thing to do is to start with your vertex. Notice that the vertex is going to be at hk, so 6, 0. So we'll start there, but with the case of up-down parabolas, then we would go 1 unit to the left of 6 and 1 unit to the right of 6, right? But with these, we want to go 1 unit above and 1 unit below, right? So that would be 1 would be above, -1 would be below, right? So let's plug 1 in. So we have notice that the simpler way of writing that is x equals y squared plus 6. For the purpose of evaluation, let me just put it in that form. So we get, if y is 1, we get x equals 1 squared plus 6, so 7. And if y is -1, we get the square of -1, which is also 1 plus 6, so 7. So we expected this kind of symmetry, of course, from a parabola. All right, pretty much everything is just turned 90 degrees around, right, compared to the regular up-down parabolas, but they work very much the same way. All right, as far as the axis of symmetry with this one, of course, it's going to be y equals k. Notice k is 0, and of course you can see it as well. So the axis of symmetry has equation y equals 0. That's a famous line, right? It's also known as the what? The x-axis, okay? And the domain and the range. Now, what are the x values that are involved in graphing this particular parabola? Notice all the x values are at or to the right of 6. So the domain of this parabola is bracket 6 comma infinity, right? Parentheses. So this half closed interval from 6 to infinity, or half open. You could call them either one, but we usually just say half open. All right. Now the range. Notice that this will eventually assume all possible y values, right? So therefore the range, unlike the domain, is not limited, and it includes all real numbers. All right, that's the set of outputs, since it's not a function, it's better to say the set of the y values that this relation would generate, right? Normally when we say output, we want to associate that with the function, right? And these are not functions, as you know. All right, so that's how you would handle that. Okay, here's another one. So if I want to put it in standard form, which is x equals a times quantity y minus k squared plus h, this would look like this. X equals, we're going to divide both sides by 5, so we end up with a 1/5 on the other side, times y minus 1 squared plus, there's no constant there, so just 0, right? So you can see here, this is k, and this is h. So the vertex of this parabola is at hk, of course, so 0, 1, right? Now the axis of symmetry is going to be at y equals k, so y equals 1. That's the equation of the axis of symmetry. And for the graph, notice that you could basically take the graph of x equals y squared and apply transformations to it, or you could just plot points. All right, if you were to apply transformations to x equals y squared, what would you do? Well, notice you would have to move it, because it's y minus 1, that means you would be moving it up 1 unit, right? And this means no movement left or right, so you would move it up 1 unit, and then you would horizontally shrink it by a factor of 1/5, right? And notice that in this case, a horizontal shrink would translate into a vertical actual stretch, right? So if it seems stretched, don't be confused, because the shrinking is happening horizontally. All right, as far as plotting points, start with your vertex, which is at 0, 1. Remember, then go, say, up 1 from that and down 1, so to 0 and 2. And plug in 2. Notice the simpler form of that is x equals just 1/5 times y minus 1 squared. So I'm going to plug in 2. So I get 2 minus 1 is 1, 1 squared is 1 times 1/5 gives me 1/5. If I plug in 0, I get 0 minus 1, which is negative 1 squared. That you get 1 times 1/5, as we expected. Also 1/5. So you plot those 3 points and you graph your parabola. Okay? That's it. All right. Try this one, see what you come up with. First, try to put it in vertex form, and then go from there. All right, I just remember that we didn't do the domain and range on this last one. So, okay, let's take a quick look at this real fast. What is the domain? The x values involved in this graph, right? They all begin right here at x equals 0 and go on forever, right? So bracket 0 comma infinity, and the range is of course all real numbers. Okay, the set of y values, right, that we end up with for this relation. Okay, let's go back. All right, since I want to put it in vertex form, I'm going to go ahead and multiply both sides by -2 first. So I get x equals -2 times quantity y plus 10 squared. And there's no constant at the end, so I can say plus 0, right? So now I know, remember, k is always, whatever you see here, it's always the opposite of that, right? So k is going to be actually -10 and h is 0, right? So the vertex is going to be at what? At 0, -10. hk, always remember. Okay, and as far as the axis of symmetry is concerned, the equation is of course going to be y equals k, so y equals -10. And to graph it, you would basically make a table, and you would start at your vertex, then go 1 unit above, 1 unit below that y value. Now, when I plug in -9, I get -9 plus 10, which is 1 squared is 1 times -2 is -2. And then plus 0 is just -2, right? When you plug in -11, same thing happens, because -11 plus 10 is -1, but when you square it, you get 1 times -2 is -2. So you would plot those 3 points and you would get your graph. Or you can do transformations on x equals y squared. Right? Because of this plus 10, that means you would want to move 10 units down, right? And because of the -2, you're going to horizontally stretch it by a factor of 2, which visually appears like a vertical shrinking. And because of the negative, you're going to be flipping it over. So you end up with this, whether you graph it or you do transformations to x equals y squared. How about the domain? Well, notice all real numbers are involved from -infinity all the way to here. So -infinity to 0. Those are the x values that are in play when graphing this relation. And for the range, again, notice you will eventually assume all possible y values. So -infinity to infinity. All right, and that's how you handle that one. Okay, for this next one, it's given to us in standard form. We'll go ahead and put it in vertex form. So we have x equals y squared plus 10y plus 21. The goal is this form, x equals a times quantity y minus k squared plus h, right? So notice that we're going to complete the square on y squared plus 10y. We need to take 1/2 of 10, which is 5, and then square it, right? Which gives us 25. So we need to add 25, And to keep the balance, we'll immediately subtract 25 as well. And don't forget you have plus 21 at the end. Now, these three here form a perfect square trinomial. So we get x equals quantity y plus 5 squared. And those two together add up to -4. There we have it, okay? So one way to graph it, take the graph of x equals y squared, move it 5 units down because of the plus 5 here, and then 4 units to the left. So you would end up at the vertex. So the vertex, as we know, is going to be, let's see, h is -4 and k is -5. So the vertex should be at -4, -5. So other than the transformation method, we could also just graph it using points. So we'll start at the vertex. We'll go 1 unit above, 1 unit below, -5 in the y column. And when I plug in -4, what do I get? I get -4 plus 5, which is 1. 1 squared is 1 minus 4 gives me -3. And -6 plus 5 is -1. Square that, you get 1 minus 4 is -3. So those are the 3 points we would graph. See, that right there is -4, -5. There is -3, -4, and there is -3, -6. Then we would just get our graph. The axis of symmetry is, of course, y equals k, so y equals -5. The line that goes right there between -4 and -6, the horizontal line. And the domain, notice it's going to start right here. Basically, it starts at h, right? So it either stops at h or ends at h, right? When it's opening to the right, it starts at h. When it's opening to the left, it ends at h, right? The domain. So bracket -4 comma infinity. The range, of course, just like the others, is going to be -infinity to infinity. All right, that's how you would handle that particular problem, okay? Make sure you can do that on your own, and let's proceed. All right, for this next one, we have a similar scenario in that we do need to first put it into this vertex form, x equals a times quantity y minus k squared plus h. The difference being, of course, that the lead coefficient in this one is not 1, so we need to deal with that first. So let me write it down over here. X equals -4y squared minus 4y plus 3. There are a couple of ways of dealing with that. One is to factor out the -4, okay? And I'm actually going to show you the way that I prefer to that method, which is I want you to divide both sides by -4. So temporarily, we will divide off the -4, and then when we're finished doing what we want to do on the right side, we'll multiply it back in. So I do recommend you actually write it down. And remember, when you divide the right side, which has 3 terms, by -4, it gets split and all terms get divided by -4. So just go ahead and throw a -4 under all terms so that you don't forget any of them. All right, so you end up with x over -4 equals, now be careful with the signs and the coefficients, so y squared plus y, right? Both of those sets of 4s cancel out, these and these. So, and then we have -3/4. Positive over negative is negative. So now we're going to complete the square on y squared plus y. Notice that the coefficient is 1. So we need to take half of 1, which is 1/2. This is kind of side work, right? And then we're going to square that to get 1/4. So we get x over -4 equals y squared plus y plus 1/4, right? And do keep in mind that we need to subtract that right away to keep the balance. So now we're just adding 0, which is perfectly legal. And don't forget we have a negative 3/4 right there. So now these three form a perfect square trinomial, and these two can be combined. So we have x over -4 equals quantity y plus, if you ever wonder what's going to go there, look at the first step of your completing the square process. That's the number that will end up going there. That's why it's important that you bring the sign of this coefficient with you as well, because then if that's negative, this is also going to become negative. But here it's positive, so we'll just go ahead. So y plus 1/2 squared. And then negative 1/4 minus 3/4, it just gives us negative 4/4, which is -1. All right, do notice that we're almost in this form, right? So now we just need to multiply the -4 back in to make the left side just x. So we get x equals -4 times quantity y plus 1/2 squared, and then -4 times -1 will give me +4, okay? So we can see here that our h is 4, k is, remember, always the opposite of whatever you see here, so -1/2. That's because you're actually looking at y minus k. So if I write it in that format, it'll be y minus -1/2, then that becomes k, okay? And that's going to make my vertex at 4, -1/2. The axis of symmetry will have equation y equals -1/2. And as far as actually graphing it, here's the table we're going to use. We're going to start at 4, -1/2. All right, normally we go 1 unit up, 1 unit down, so no reason to change that here. So -1/2 plus 1 gives me 1/2. Minus 1 gives me -3/2. So when I plug in 1/2 for y, right, I end up with 1/2 plus 1/2, which is 1 squared is 1 times -4 is -4 plus 4 is 0. And when I plug in -3/2, I get -3/2 plus 1/2, which is -2/2, which is -1 squared is 1, right here, times -4 is -4 plus 4 is 0 again, okay? Pass the check. So these are my 3 points, 4, -1/2, right? Zero 1/2 right there, and 0, -3/2, which is the same as -1/2. So this point, and the vertex is what we use to graph it, okay? So what else do we need to do? Domain and range, right? So the domain is going to be basically -infinity all the way up to what? To h, which is what? 4. Bracket, include the 4. And the range is -infinity to infinity. And that should do it for this one. In case you want to do transformations, you can do that as well. You're going to take the graph of x equals y squared. You're going to move it half a unit down, 4 units to the right. You're going to horizontally shrink it by a factor of 4. I'm sorry, horizontally stretch it. My bad. 4 times 4. So horizontally stretch it by a factor of 4, which makes an appearance as a vertical shrinking. And then you're also going to reflect it, right? So with respect to its axis right there, okay? So notice that you would end up with exactly the same graph as you did with us plotting points. Reflection, of course, being with respect to the line x equals 4. All right, so make sure that you're comfortable with that and we'll proceed. Okay, next we want to look at a different way of defining a parabola. We call it the Focus-Directrix definition of a parabola. A parabola, in this sense, is the set of points in a plane equidistant from a fixed point and a fixed line. The fixed point is called the focus that you can see right here, and the fixed line is called the directrix, which you see down here. So basically, you take all the points so that they have the same distance from both that point and that line. And what you end up tracing is exactly a parabola, okay? So it is possible to find an equation of a parabola which has a vertex at 0, 0 entirely from this geometric definition. So here's what we're going to do. Firstly, in case you see something a little different from this, I don't want you to be confused. Some authors and books and websites, they treat P as a directed distance, so that a directed distance can be positive or negative depending on the direction you're moving. But I have found it much less confusing for students if I just let P be positive and to represent the distance, this distance between the focus and the vertex, which should be the same as the distance from the vertex to the directrix, right? The perpendicular distance from the vertex to the directrix, okay? So notice that if we choose that option and we always consider P to be positive, then this length down here will represent the point negative P on the y-axis, so that the directrix will have an equation of y equals negative P, okay? So let's see how we can use this information to actually come up with an alternative way of defining the equation of a parabola. Here, what we're going to let P of xy be a point on the parabola, just like that right here, okay? Then by definition, we know that the distance from P to the focus, which is at 0, P, is the same as the distance from the point to the directrix, the perpendicular distance. In other words, drop a perpendicular to the directrix, that's the distance you measure. That's just by this new definition we suggested for a parabola. So what does that mean? Well, applying the distance formula, right, to P and F, we get, remember, the square root of x2 minus x1. So here it'll be x minus 0 squared plus quantity y2 minus y1. So here it'll be y minus p squared. And on the other side, we're going to write the distance between P right here and D, this distance, right? Now, because this is obviously the point xy, that means the x value here is x, and we know the y value. The y value on this entire line is negative P. So the y value will be negative P. So now apply the distance formula to these 2 points. So we get x minus x squared plus y minus negative P squared, right? So we end up with the square root of x squared plus quantity y minus p squared, because x minus 0 is just x. On this side, this is of course 0, so we end up just with quantity y plus p squared. Now we can go ahead and square both sides, and we'll get rid of the radicals, And we'll also go ahead and just expand this, right? So using the formula we've seen before, that's going to be the first one squared minus 2 times the first times the second plus the second squared. So that's where this y squared minus 2yp plus p squared comes from. And on this side, the square root goes away because of the squaring, and we just expand this to be y squared plus 2yp plus p squared. Now notice p squared cancels p squared, right? And y squared cancels y squared. So we end up with x squared, and we move the negative 2yp to the other side, becomes 4py. So yp or py, same thing, right? So notice that this right here is the new definition for a parabola which we can use. And what's interesting in it is that the p in it is exactly the distance between the focus and the vertex, which is the same as the distance between the vertex and the directrix, the perpendicular distance. Now, if you solve this for y, you end up with y equals 1 over 4p x squared, which is the familiar form ax squared that you're used to. So no matter what approach you take to defining a parabola, the end result is going to be equivalent, but they're just interesting different approaches. So let's see if we can tackle a few problems with this understanding. Before we do so, just keep in mind that because we're always considering p to be a positive distance, right, between the focus and the vertex and the directrix, then when you flip it over, right, rather than the equation becoming x squared equals 4py, it's going to end up being negative 4py, right? So when you're looking at this, start with this equation and approach the problem. And when you're looking at a right side up one, approach it with this. I just like the positive p because it's a lot easier to find from the graph for most students, okay, and most people. All right, so when you are upside down like this, notice that this is going to be y equals p. The focus is going to be at 0, negative p. And this distance, of course, is going to be the same as that distance as well. All right, so this is a reflected parabola. So to summarize, let p greater than 0 be the distance from the focus to the vertex, as well as the perpendicular distance from the directrix to the vertex. The parabola with vertex at 0, 0, focus at 0p, and directrix at y equals negative p, this one, has equation x squared equals 4py, and it opens upward. The parabola with vertex at 0, 0 as well, focus 0, negative p, and directrix y equals p, has equation x squared equals negative 4py, and it opens downward. The vertical axis of symmetry of both of them will be the y-axis, which has equation x equals 0. All right, next we want to find the focus, directrix, and the axis for this parabola. Now, when you define a parabola in the way that we just did, for some reason we've decided we don't usually call it the axis of symmetry. We just call it the axis. So let's go ahead and find the focus, directrix, and the axis for this parabola. Notice that I brought this over so you could remember. We're dealing with this kind of a situation, right? So the equation of choice is going to be x squared equals 4py, right? So we start with x squared equals 4py, and here we're dealing with x squared equals 8y, so that means 4p must be equal to 8, right? So that makes p equal 2. Now that you have that, you know that since the vertex is clearly here at 0, 0, the focus is just going to be at 0p, so 0, 2, right? All you have to remember is that the distance from the vertex to the focus is the same as the vertical distance, the perpendicular distance from the vertex to the directrix. All right, so that makes the vertex obviously 0, 2, right? And the directrix is going to be located on this horizontal line exactly 2 units below the x-axis, right? So the directrix is going to have equation x equals -2. The axis of this particular parabola is obviously going to be the y-axis, also known as the equation x equals 0. Okay, so that's how you do that. All right, go ahead and try this one. See what you come up with for the focus, directrix, and the axis for this parabola. All right, notice that this is an upside down parabola, right? So this is going to be the model we're going to use, and the equation of choice is going to be in this format: x squared equals -4py. So if I try to put this equation in that format, that means I would keep the 5x squared on the left side, and I would move the y to the right side, so it becomes -y. I need to get x squared by itself, so we divide both sides by 5, so we get x squared equals -1/5 y, right? So that tells me that -4p should equal to -1/5. And if I multiply both sides by -1/4, I end up with p equals +1/20. So because the vertex is at 0, 0, I know that the directrix is going to be exactly 1/20 units up, and the focus is going to be exactly 1/20 units down from there, right? That makes the focus at 0, -1/20. And the equation of the directrix is just going to be y equals +1/20. And that's all there is to it. See how easy it can be if you approach it the right way with the right graph. One more thing, the axis. What would the axis be? Well, the axis is right there, so it's just going to be the y-axis once again. Or the equation x equals 0. Okay, that's how you do that one. You can handle parabolas with horizontal axis of symmetry in the same manner that we just did with the vertical ones using p. So again, we let p greater than 0 be the distance from the focus to the vertex, as well as the perpendicular distance from the directrix to the vertex. Better to say probably the vertex to the directrix, because we're dropping a perpendicular from the point to the line. So just keep that in mind. The parabola with vertex 0, 0 and focus at p0 as depicted here, and directrix x equals -p, this vertical line, is going to have equation y squared equals 4px, and it opens rightward. Okay, the parabola with vertex at 0, 0 with focus at -p0 and directrix x equals p will have equation y squared equals -4px, and it opens leftward. Okay, and this is all contingent on considering p greater than 0 to be the distance, not the directed distance, but the actual non-negative distance, positive distance, right? Even beyond non-negative, it's actually positive. The vertical axis of symmetry of these parabolas is going to be the x-axis, which has equation y equals 0. Okay, I just pasted this here for you just so you can see how similar the analysis is, right? With these vertical ones, the square is on the x, right? And on the other side, you get 4py. With the horizontal parabolas, the square is on the y, and you get x on the other side, right? But we handle everything else pretty much the same way, right? So just it's very, very similar. Just, these pair are obviously vertical ones. These are horizontal ones. All right, let's go ahead and find the focus, directrix, and axis for this parabola. Now, since the square is on the y, we know that this is going to be one of these horizontal parabolas. And since we have it opens leftward and we have a negative there, we know we're going to be using this formula, right? So we start with y squared equals negative 4px, and since we have y squared equals negative 6x, that means negative 4p equals negative 6. So therefore p equals, divide both sides by negative 4 and simplify, you should get 3/2, right? So this means that the vertex is right there at 0, 0, and the focus is going to be exactly 3/2 units to the left of that. So at negative 3/2, right? So the vertex, the focus, well, we know the vertex, right? The vertex is 0, 0. So the focus is going to be at negative 3/2, 0. Now the directrix is going to be exactly 3/2 units to the right of this, right? So that's going to be at positive 3/2. And it'll be a vertical line, so the equation will be x equals 3/2, right? And the axis, of course, for these is going to be the x-axis itself, also known as the line y equals 0. Okay, so there's a horizontal one for you. All right, next let's go ahead and generalize this notion to the translated parabolas. Basically, instead of just having x squared equals 4py, we're going to have the translated version. We're going to have quantity x minus h squared equals 4p times quantity y minus k. And same here for the upside down one, we're going to have quantity x minus h squared equals negative 4p times y minus k. Once again, we're letting p greater than 0, so positive p to be the actual distance from the vertex to the focus, as well as from the perpendicular distance from the vertex to the directrix. Okay, now just so that you realize this is very much no different from what we've done before, I'm going to take one of these and I'm going to put it in a more familiar format for you. So look at quantity x minus h squared equals 4p times y minus k. Remember that with this kind of parabola, our vertex form, we used to have this form, y equals a times quantity x minus h squared plus k, right? Well, you can actually transform this to this form. Watch. Just multiply both sides by 1 over 4p, so you get and then move the negative k to the other side. So you get y equals 1 over 4p times x minus h squared plus k. Notice, I have the y on the right side, but that's not a big deal. You can always write the y on the left side if you want. Remember, if a equals b, then b equals a, the symmetric property. All right. So notice very much similar to this is 1 over 4p. Okay, so this actually tells you an interesting connection or relationship between 1 over 4p and a, right? 1 over 4p is exactly a, and you can, given a, you can find the p as well. All right, so there we go, and that's how we generalize. And for the left right ones, very similar, right? The only thing that changes is, you know, instead of having quantity x minus h squared, you have quantity y minus k squared, etc. equals 4p times x minus h, and we'll use minus 4p times x minus h here. And you can take each one of these and do the same thing to it, and notice that you can get the more familiar form that you are used to already. All right, now, the nice thing about using a positive p, you don't have to memorize all this stuff, right? You don't need to sit there and worry, oh, do I go plus that? All you need to know is this relationship, that this distance from the vertex to the focus is the same as this perpendicular distance from the vertex to the directrix. That's all you need to know. And you can handle pretty much any problem after that. All right, let's try this one. We're going to try to find the focus, directrix, and axis for this parabola. Now, we notice that this is a rightward opening parabola, so the general equation of interest for us is going to be quantity y minus k squared equals 4p times x minus h. Okay, so we notice that 4p must be the same as 8. So 4p equals 8. That's going to solve for p for us to get 2. So from this equation, we can tell the vertex is shifted and it's at 4, -5. So the vertex here is at 4, -5. Remember, the focus is going to be exactly p units away, and it'll be to the right. So all you have to do is add 2 to the x value of the vertex, right? Because that'll shift it 2 units to the right, right? So 4 plus 2. So the focus is going to be at 6, -5. Now, for the directrix, you're going to actually go 2 units to the left, right? Directrix will be to the left of that, and you will have the vertical line going through 2. What's 4 minus 2? 2. So you get x equals 2. All right, so remember, we got the 6 here by doing 4 plus 2, and we got the 2 here by doing 4 minus 2. I told you, all you have to remember is the fact that the distance between the vertex and the focus is exactly the same as the distance between the focus and the directrix. All right, so there's the directrix. How about the axis? Well, the axis you find just like we did before. It's just going to be y equals k, right? So k is -5, so right there. So y equals -5. All right, before we leave that problem, I wanted to show you a better graph. Notice that here we have the parabola. Here is the axis, right, at y equals -5, right, like we said in the previous screen. And here we have the vertex at 4, -5. Here's the focus at 6, -5. And the directrix That's better. I had accidentally typed a negative on the 2. So the directrix at x equals 2. Notice this distance between the focus and the vertex is exactly the same distance between the vertex and the directrix. Okay, and of course that's the perpendicular distance, right? That's how you find the point, the distance between a point and a line anyway, right? Anytime you have a line and you want to find the distance from a point, you take the point and drop a perpendicular to the line, because you obviously always want to calculate the shortest distance between the point and that line, right? Otherwise, I can say, oh, the distance is from here to here. No, that would not be called the distance between this point and this line. It's always the perpendicular distance. Okay, and there is that. So let's go ahead and move on. Okay, go ahead and try to see if you can find the focus, directrix, and axis for this parabola. Okay, so we notice this is an upward facing parabola. It's shifted over, it's translated, but nevertheless we know the form, so it's going to be of the variety quantity x minus h squared equals 4p times y minus k, right? So that means 4p must be equal to 24, which makes p equal to 6, right? Now we know that the vertex is at 4, negative 5, right? Because that's h and k is negative 5, right? So in order to find the focus, we know that whatever y value we're at, we're going to go exactly 6 units up, because the axis is going to be at x equals 4, right? So we're going to go exactly 6 units up from where the vertex is. The vertex is at y value negative 5, so we add 6 to that. So we end up with the focus being at 4, 1. Remember, where that 1 comes from is negative 5 plus 6. Now, to get the directrix, we're going in the opposite direction. So we're going to start at the negative 5, and we're going to go 6 units down on that axis line, right? So we're going to have the equation being, well, this is going to be a horizontal directrix, right? So y equals negative 11. And remember, where that comes from is just the y value of the vertex minus exactly the same amount, p, 6. There is that, right? We know the axis, and that should do it, right? So we needed the focus, directrix, and the axis. So you see, you didn't have to memorize any of that stuff with the where the directrix is going to be and all that. You just figure it out. All you have to know is that the distance between the vertex and the focus is exactly the same as the perpendicular distance from the vertex to the directrix. That's it. All right, so for this one, we want to find an equation for this parabola. We know the vertex is at the origin 0, 0, and the focus is at 6, 0. So somewhere around here, right? So we know that this distance is going to be exactly our p, right? So they're giving us p indirectly. P is equal to 6, right? Now, this is a rightward opening parabola, so we know the general equation that we need to use is y squared equals 4px. Of course, this is a horizontal one, that's why the square is on the y, and since the center is at 0, 0, we don't need to do the more general form of y minus k squared equals 4p times x minus h, right? So this is good enough. I mean, we could, it's just that we would put zeros for h and k, and we would end up with this anyway, right? So all we have to do, this is like a almost trivial problem, right? All we have to do is just plug in 6 for p. So we get 4 times 6x. So we get y squared equals 24x. And that's all we have to do there. Okay? All right, so in this one, what they're giving us for this parabola is the directrix, and they want us to find the equation. Notice it does go through 0, 0. So, well, if the directrix is at y equals negative 1 over 44, right? That means, let's say the directrix is right there. Forget this 5. Let's say it's not drawn to scale, right? This distance right there is going to be exactly 1 over 44, right? And that distance is p, right? So p equals 1 over 44. And this is a vertical parabola and it's right side up. So our equation is going to be of the form x squared equals 4py, right? So all we have to do now is go ahead and replace p with 1 over 44. So we get x squared equals, that's going to cross cancel and give us 1 over 11y. Now, if you want a more familiar format, you can multiply. Now, this is good enough, right, for the answer. But if you wanted a more familiar format, you could multiply both sides by 11. You would get 11x squared equals y, which is the same as y equals 11x squared. See? That's another format you could give the answer in. All right, so in both of these problems that we just did, basically they're giving you the value of p indirectly, and then the rest just flies off, right? Okay, let's go ahead and try something else. All right, go ahead and see if you can find the equation of this parabola. It has a vertex at the origin, and it passes through the point square root of 210. Now, my hint to you is that they're not giving you p, and you have to find it. See if you can find it. All right, so it's right side up, right? And it's a vertical one. So we know that the equation of choice is going to be x squared equals 4py, right? But they give us a point. So we're going to use x equals square root of 2, y equals 10 from the given point, which is on the parabola, to find the value of p. So instead of x, I'm going to substitute square root of 2. And instead of y, I'm going to substitute 10. Now all we have to do is solve for p. So we get 2 equals 40p. Divide both sides by 40. So you get p equals 2 over 40. Or p equals 1 over 20. So we have x squared equals 4 times py, right? So times 1 over 20y. So we get x squared equals 1/5 y. Now that's one form, and if you want to multiply both sides by 5, you could. You get 5x squared equals y, or y equals 5x squared. So there is another form, and that's how you do that one. All right, so how about this one? They want us to find the equation of a parabola with a vertex at 3, -2 and focus at 3, -4. So in other words, we have 3, -2, and then somewhere down below we have 3, -4. Notice that that means we should be able to find p. That's going to be the distance between these 2 points, right? And of course, this is a vertical distance, so we're going to subtract the y values. Since p we're considering to always be positive, we're going to do the larger number minus the smaller number. So -2, p is going to be -2 minus -4, which is going to be -2 plus 4, which is 2. So now all we have to do is write the equation, and we need to know the right form. This is an upside down parabola, vertical, so it's going to be of the variety x minus h squared equals negative 4p times y minus k. Now, we know that h is 3 and k is negative 2 because that's where the vertex is, right? So we get x, quantity x minus 3 squared equals negative 4 times p, which we now know is 2, times y minus k, which is negative 2. So let's make it look nicer. We get quantity x minus 3 squared equals negative 8 times y plus 2. And that's basically the equation. That's all we have to do. All right, so in this one, we want to write the equation of a parabola with a vertex at negative 2, 1, and directrix at negative 10. X equals negative 10. So, in other words, we have negative 2, 1 for our vertex, right? And the directrix is actually, in this graph, it's this line right here, right? So this point on the directrix, which is going to be exactly where the perpendicular from the vertex to that directrix would land, is going to be at negative 10, and of course the same height, 1, right? So basically, to find the distance, which is going to be p, we're just going to do the larger number minus the smaller number to get the distance. So p is going to be, and these are x values, we're going to be subtracting negative 2 minus negative 10. So we get negative 2 plus 10, which is 8. All right, so it's a rightward opening parabola. So we know that the general form, well, the vertex form for it should be y minus quantity y minus k squared equals 4px. But because it's, rightward, so it's going to be positive 4p times x minus h, right? 4p times x minus h. All right, so now we plug in what we know. So basically, y minus 1, notice h is negative 2 and k is 1, right? So y minus 1 squared equals 4 times 8, which is p, times x minus negative 2, right? If we clean it up, we get quantity y minus 1 squared equals 32 times x plus 2. And there is our equation. Notice if you, for some reason, wanted that in a more familiar form, you could always divide both sides by 32, so you would get 1 over 32 times y, quantity y minus 1 squared equals x plus 2, and then move the 2 over to the other side, so you would get 1 over 32 times quantity y minus 1 squared minus 2 equals x, or if you really want it to look familiar, just write it with the x on the left side. Like that, okay? So this is more like the x equals a times y minus k squared plus h format that you may be familiar with, okay? And that's how you do that one. All right, we're going to look at a couple of applications and then call it a day. A laboratory designed a radio telescope that had a diameter of 280 feet. So from here to here is 280 feet and a maximum depth of 36 feet. So this depth right here is 36. write an equation of a parabola that models the cross-section of the dish if the vertex is placed at the origin and the parabola opens up. Okay, so first we should figure out what this point xy is, because remember, if from here to here is 280, that makes this much, which is going to be the same as this x value, 140, right? And we know that this depth right here is 36. So that means the y value right there is 36, right? Now, it's an upward facing parabola with center at 0, 0. So we know the equation is going to be of the variety x squared equals positive 4py, right? So if we go ahead and plug in this for x and this for y, we should be able to get p, right? So we get 140 squared equals 4p times 36. So p is going to be 140 squared over 4 times 36. So let's go ahead and compute that. Okay, so we have 140 squared divided by 4 times 36. And if we hit the A and B over C button, it will give us the fractional version. So we get P is equal to 1225 over 9. All right, so we're ready to go ahead and write the equation of this parabola. So we get x squared equals 4 times p, which is 1225 over 9 y. So x squared equals, let's go ahead and multiply 4 by 1225. We get 4900. So 4900 over 9y. Okay? Or you could, multiply both sides by 9 over 4900 if you want to write it as y equals some number times x. Or x squared rather, right? You would just end up with y equals 9 over 4900 x squared. Either way is fine. Okay, so that's part A. In part B, we say the receiver must be placed at the focus of the parabola, right? So how far from the vertex should the receiver be located? All right, so that means it's going to be somewhere around here, but remember, that's just going to be the value of what? P, exactly. We know what P is. So for part B, it's just going to be 1225 over 9, and these units are in feet, right? Now, since, you want an actual answer, it's better to just get an estimate for that. So we go 1225 divided by 9, so approximately 136.1 feet above the vertex. Okay, so yeah, don't let the words scare you. Most of the time these applications aren't that bad. You just have to relax and see what's given and then just apply the knowledge. It's really not too bad. All right, let's do one more problem and we'll call it the day. All right, so here's the last problem we're going to look at. We have an arch in the shape of a parabola that has the dimensions shown. And we want to know how wide is the arch 3 feet up, okay? The trick to this problem is going to be where you place your axes. And the cleverest place to place it is so that the vertex of the parabola is at the origin. So let's go ahead and draw that. Give me a second to draw that. All right, so I just drew a couple of vertical, perpendicular lines here. So this is going to be considered our 0, 0. And the trick to finding the equation of this parabola to begin with is, because we're going to want the equation in order to be able to compute what they want us to compute. But the trick is to find one good point on the parabola other than the vertex, so that we can go ahead and find P. Notice that if this entire piece here is 6 feet, given that I'm starting at 0, 0, that means that's going to be 3 feet and that's going to be 3 feet. So moving this way, this right here is going to be at x value 3. Now, I know that this is going to be 5 units below the x-axis, so the y value here will be -5. So this point here will actually be at 3, -5, right? So let's look at the parabola and decide what form we're in. It's an upside down parabola centered with vertex at the origin. So it's going to be of the variety x squared equals -4py, right? And now we have a point, so we can plug in 3 for x, so 3 squared equals -4p, and we're going to plug in -5 for y. So we get 9 equals 20p. So p is equal to 9 over 20. So basically I get x squared equals -4 times 9 over 20, which is p, y for the equation of the parabola, or x squared equals, cross cancel the 4 and 20, they leave you 5 down below, so -9/5 y, right? So now I want to know how wide this arch is 3 feet up. So if I remember, this elevation here is -5, right? So if I go 3 feet up, I'm going to be at what elevation? At elevation -2, right? So basically I need to find out what x value corresponds to that on the parabola. That will tell me what that length is, and all I got to do is double it to find out how wide the parabola is. That's the game plan, okay? Let me make that a little bit nicer. Not really. Let's try one more time. Okay. It's the end of the video. You know how I get at the end of the videos. Okay, so basically we're going to be plugging in -2 for y in order to get the x value. So we get x squared equals -9/5 times -2. Remember, you're going 3 feet up. This is 3 feet. And you're at elevation -5 to begin with. So what's -5 plus 3? That's -2. That's why this elevation here is -2. All right, so we get x squared equals 18 over 5. Oh. So x is going to be, well, positive or negative square root of 18 over 5, but I'm only interested in length, so I'm only going to use the positive case. But remember, the width I'm looking for, this width, that's actually going to be, the width I'm looking for is going to be 2 of those x's, right? So now we're just going to plug in and compute. So we're just basically going to compute 2 times the square root of 18 over 5. And we get approximately 3.79 feet. So that's how wide that parabola is, 3 feet up inside the arch. Okay, so that's pretty much it. That was quite a few problems, but you know, I needed to do some so you would know how to handle them too, as well. Or in case you need to, you know, reference, you should always try to handle all these problems on your own first, and that should do it. So take care until the next video.